All right. Hi, everyone. Welcome to our final session on variational inference. So today I thought I would try and do a quick recap before turning things over for us just to talk about a few more of the concepts. It's such a big topic. We could spend a whole, you know, 12 session series on just VI. So we're just going to cover some of the high level aspects of what you need to understand. So in this entire part that we're talking about this spring, we're talking about Bayesian inference, and so in particular, can we calculate the posterior? Um, and so I was thinking about this, and the next chapter is Monte Carlo, and it actually talks about sampling. So I think the easiest thing that you could do is, rather than having to do some complex calculation, is you could just do a whole bunch of sampling, and you could just sort of empirically see what the distribution looks like. Um, but the problem with that, I'm pretty sure when we read the next chapters starting next week, is that it's very sample inefficient, and maybe you need to do zillions and zillions of samples. What if you have like an image, right? And it's whatever, 200 by 200 pixels, so 40,000 floats. Like, that is a very high dimensional. R 40,000 is very high dimensional space. How are you going to sample across R 40,000, right? Um, so at the super high level, variational inference is, instead of directly sampling that, what we're going to do is we're going to propose a family of distributions. We'll call that family capital Q, and Q will be parameterized. So let's say it's a Gaussian, you just have basically a few, you could do, depending on how you parameterize it, but you could have a few means and a few variances, and voila, you're done. Um, so so basically what we can do is we can do some samples, and we can sort of check the difference between the prediction from uh, um, our proposed distribution Q and the data that we're seeing. And so what we do is we do the KL divergence between Q and the posterior. And a really nice thing happens when we do the KL divergence. So to directly calculate this posterior, we need the evidence, and that's this nasty integral we need to compute in order to get P of X. So when you do the KL divergence between the two distributions, then basically that P of X term goes away because it's the same for all KL divergences. And so you can essentially just compare two KL divergences, and you never need to calculate that because you're gonna subtract it one from the other, and it's going to zero out. So I would say at a super high level, that's where variational inference affords us some convenience over directly sampling. So now, instead of, you know, R whatever 40,000, maybe I have a whatever 100 or less dimensional Q distribution. And so I can make the problem smaller, and then I can also actually more easily compute this evidence-based lower bound, this elbow, in order to estimate the KL divergence. So we can use that trick, and eventually what we're going to talk about with the focus on deep learning here is that you can use a neural network to estimate the parameters for your distribution instead of just doing it in a manual way. And so then ultimately what we're doing is we're taking whatever signal we have about whether or not our proposed Q distribution looks like it matches the sample or not. We take that and we back propagate it into the parameters of our neural network. And I believe in the book they're called thetas. So ultimately, as machine learning, deep learning practitioners, this is what we're used to doing: is we build a neural network with a bunch of weights. We call those parameters theta, and we just run back propagation. So the real trick is that variational inference tells you the loss function, the target that you're using for your neural network, so that ultimately you just take that signal and you back propagate through your neural network. All right, so I'm going to turn things over to you, Dave. I don't know if you have any color to add, if you thought that was not one paragraph, but if you thought that was a decent recap of just sort of the big picture, what we've been trying to talk about with VA.
That is excellent, Ted. Uh, this, as has been mentioned before, this is a big, complex topic. There's no easy way to cover it from scratch, if you may, and go to the level of complexities that this book covers in such a short time. But that's a good summarization. So at the end of the day, it is an optimization problem, and there are different techniques to get this posterior, and VI is one of those. This chapter will cover one or two more, expectation propagation and others, which will not go into too many details of. But essentially, getting the posterior to MCMC or VI or EP or Laplace approximation or whatever other techniques that exist out there are to find this posterior so that we can have a better understanding of the data distribution that we can then use for generative modeling or whatever else from the latents, rather than having to understand the humongous dimension original data set. And the only thing I'll add is that this theory and these theories are the essence or the core of the entire work, more or less the entire work that is going on in the generative modeling side, all the way from whether it is the LLMs, where you are, approximating the next character or word or token, but absolutely for images where whether it's GANs or UAEs or diffusion models or normalizing flows, all of those theories are the foundation for the generative AI that we see out there. So humongous work going on for last several decades, and we'll do whatever we can do.
And so with that, I'm just going to make a quick plug. So the plan is in the fall, we are going to talk about generative models, and that's part 4 of the book. And so the plan is, like, come September, we're going to talk about GANs, diffusion models, all the stuff that goes into more detail and specific to these image generation models at the end of the book.
All right, so if we are ready, then I will pause my video and share the screen. Do I have the screen share right?
Yes, I just turned it on.
Go to the... Okay, so I will just very quickly show this famous picture that we have, which Ted was describing, where we have X is our data. X is the data that we are trying to understand the distribution of. Z is the latent that will help us understand it better with the help of a smaller dimension Z. And the whole idea is to understand the distribution of Z so we can understand the distribution of our data X. And in order to get the distribution of Z, since it could be a intractable complex distribution, we try to approximate with Q, with a family of Qs, which is shown in this circle over here, and try to find the Q which is closest to P, and the closeness is determined by the KL distance between the Q estimated posterior for Z versus the actual posterior, which is measured using a function called elbow, which we try to maximize. Elbow is the evidence lower bound, and O is for optimization. So the entire set of techniques for VI are to optimize elbow, maximize elbow, and optimization techniques for that. There are 2 different kinds, fixed form variational inference and free form variational inference. Fixed form is where the parameters, the free form is where you have set of parameters that are independent. So, you can have a, for independent parameters, you can have a product of those to get the actual likelihood for your data given the Z. And we'll cover the free form in detail, which is also called the mean field assumption. We'll see that. We had looked at this in the last meeting, so I'll skip this one. I think what I want to do very quickly is to, we have covered much of this, so I want to quickly jump to the equation that we are, so elbow is what we are trying to maximize. So sorry if the screen is moving a lot here, but essentially we are trying to optimize elbow. And when we are trying to optimize the elbow, the idea is that if we take the derivative with respect to parameters, and there are two sets of parameters, which I'll come to soon. Once we take the derivative, and the idea is to find the maximum value of alpha or the evidence lower bound, so that we get the parameter values theta and psi, which will give us the optimized distribution. So when we take that derivative, and let me jump to that part. So for example, this is our elbow function, and this what happens is we have to optimize for, in this case, theta is the model parameters for our data and the whole model that we have. The way we have defined our model, it could be, and then let me just quickly show different forms of models. So on the left, what we have is a graphical model with, for each observed data, we also have a latent variable, and then there is a global variable, versus there could be a different kind of model that we can come up with for our problem, where we have observed variables and no local variables, but just some global variables. Makes the problem solving different, and in each of those cases, if we have one-to-one correlation, then what you see below is theta, and then there are parameters corresponding to I mean, psi in this case is all the parameters for Q possibly. But what happens is that then we have to estimate all the parameters for all the Z's and the thetas. But if it is only, and there is a direct correlation between each of the data point to the latent variables. But if we have global variables or abstracted variables, then we do not have to have that one-on-one correlation in terms of estimating those parameters. So when we are trying to estimate those parameters, let's say we have for n data points, we are trying to estimate the local variables, and each one of those has, let's say, psi parameter, and since there are n of those, psi n parameters. And using the stochastic optimization approach, where if our estimator is unbiased, then we can take the stochastic approach, and instead of finding the optimization for psi n for so psi n, let me point out two things. So psi n includes both, in this case, it includes the local parameters, but we also have in our elbow function, we also have theta, if you look over here, which is our global parameter. So we are trying to find out both. And if our estimator is unbiased for the objective function calculation, then we can use the stochastic approach, and we can have our evidence lower bound computed using this. And in this case, we are, as we had looked at it last time, I have a good picture, but I didn't take a copy of it. I'll point out at the end of this, the video by David Bly in NIPS or NeurIPS 2016. they had a very good image trying to describe a stochastic variational inference picture there, where how the local variables were estimating each of the science, but then the global variables were being optimized in more like instead of one-on-one optimization or estimate for science for each of the data points, they could be estimated depending on the batch every time. In the
So Dave, before you
yeah.
move on, like this equation 10.27, I think we can think about, again, just trying to make sure people have sort of a high level intuition, right? There's a lot of symbols in these equations. This whole book is very dense. But we can think about it in terms that people are used to if you're doing deep learning, okay? So theta is the parameters of your neural network. If you really need to know theta and psi, if your neural network is predicting the size for a given theta, then you don't need psi separately. You just need your thetas, okay? So we'll build a neural network, and again, conceptually, you can just think my neural network inputs theta and it outputs psi. And if we know theta and psi, then we have all the parameters we need for our target distribution Q. Okay, so given set of thetas and psis, that fully determines what our Q is, which is again approximating approximating our posterior. That's our desired. So what you see on the right hand side of the equation, n over b, basically that's just we take a mini batch. Okay, we're not going to use the entire data set. We're going to do mini batch gradient descent. And so if my batch size is whatever 64, then that means I'm going to take 64 samples. And so then obviously my loss will be 64 times bigger than with one sample. So that's why you see the divided by b. Okay. But so then basically we just take a look at our elbow over this batch of examples, and voila, we can say we can estimate what that loss would be over the entire data set of n by dividing by our batch size and multiplying by the number of samples that we have in the entire. So we can either do per sample or we can do per, everything. So he's showing the form where it's per everything, which is just n over b. If you wanted to do per sample, it would be 1 over b. They're equivalent, basically. But so anyway, so that's all that we're doing here is we're saying we're taking a mini batch, and ultimately we're going to apply gradient descent to equation 1027, and we're going to use gradient descent to refine our parameters theta of our neural network. So that's kind of it in less mathy terms, more in just sort of plain English terms.
And with that, maybe I will, no worries, yeah, jump to the actual algorithm for where the gradient descent is applied. And over here, the gradient, so what happens is, let me kind of spend just 30 seconds more on equation 10.27 up there. So right there, 10.27. So while we can go through the iterative steps to optimize size and thetas to get the point estimates that will optimize for our model for posterior, for estimating posterior. It can take very long given the number of data points and the number of variables involved. And the same presentation that I talked about, David Blythe, who is one of the gods of VI field, in that presentation, he does show that trying to solve it just as is without any optimizations, let's say even before solving with the stochastic, it takes very long to even get the first reasonable estimate, because you have to look at the entire data before you get any estimate for psi and theta. With stochastic, you can start estimating theta even with a few data points, so few psis for few data points, and then start estimating theta, and you start converging really faster compared with stochastic VI. And then the challenge there is that you still are looking at each data point to estimate size for each of those hidden variables. And instead of trying to estimate individual size in each with individual data point, how about if there is another model which is modeled by psi n, phi, and inferencing model phi that takes any xn, and for the given xn it will output psi n, and it could be a neural network, it could be anything else. So now if that is the case, then what we are trying to find is that instead of estimating Zn with Qn, we are estimating Zn with this inference network for applied on Xn. And that is what will help reduce the cost of computation even further to estimate psi n in this case. However, and this is called the amortized VI because we are size are being estimated and getting for each of the ends basically estimated based on the inference network rather than exact point estimate that you would get in this 10.27. So if we continue on this path, this is the algorithm that we have, 10.1. We initialize the theta and now the phi, which is the inference network. We sample, we pick a data point xn from the data set. We apply the expectation step, which is the finding the phi or optimizing for phi based on the data point that we picked. And then in the next step, we optimize the theta. So if you look at it, we are optimizing for phi in this step. Once we have the inferencing network optimized, then we use that to optimize for theta, and then we keep on repeating that till we converge. In this particular case, we have phi estimated with a neural network, and we could have theta also estimated with a neural network. But the point of phi and theta here is whether neural network or not. Those are not those are an estimate for mapping for each local latent variable based on phi rather than based on the original psi n that we had. That's a mouthful, and I'm sorry if I'm repeating it in convoluted way. The only reason I'm trying to repeat in many different ways is because it is a complex topic. So please, I apologize if I'm still not very clear, but things are getting clear in my mind and trying to relay as best as I can. So feel free to interrupt if you have any questions as well, but this is still touching the very basics and we have a lot to cover.
Hey, Dave.
Hi,
Do
Ranjit.
they talk about how they sample this xn from this probability distribution?
This is the data set that you're given. So in the worst case, you have to go through all of those. So in this specific case, they do not talk about that, because if you want to estimate the z's for all your data points, then you have to look at all of those. I think, if you're doing stochastic approach, then you are essentially looking at a batch at a time and optimizing for that by looking at the batch at a time. But
so I guess randomly selecting given n data points, right, from their entire data set.
Yeah, and in all likelihood, it is like, trying to, when you're going from an epoch to in a neural network scenario, or in any other scenario where you have to cover the entire data set and you're iterating the entire data set multiple times, you're trying to change the bag of batch that you're getting every time so that it induces variability and then forces you, regularization basically for learning the phis and data.
So thanks, Dave. That was a really good question, Ranjit. So I think what I might have said a little earlier, Dave, I jumped the gun a little bit, and so if that confused anybody, I apologize. So what Dave said for algorithm 10.1 is exactly right. So if you heard something different from me, you should you should pay attention to what's on the screen and what Dave said. So I think at this point in the chapter, what we're saying is that our latents are in a low enough dimensional space that we can afford to just sample randomly, which was your question, Reggie, right? So for line 3, where it says just sample, it's just completely randomly sample. What we will see later on is that for some other techniques, it's important how we do the sampling, and you can't. But I think right now we're just assuming that there might even be a few tidbits later in chapter 10 where they talk about some tweaks. But right now, yes, just completely just random samples.
Yeah, I was asking from that point of view. Yeah, thank you.
Yeah. And if you look at like variational autoencoders that are trained to generate images, they do, in fact, sample completely randomly.
Though I do want to clarify, in this case, they are talking about sample xn. In VAE, they typically are talking about sampling the latent. So this is not the sampling of the latent, but the sampling of the actual data. And there are techniques. There's a small hint in this chapter, which will be covered in next chapter, on how to build actually a neural network for the latent sampling as well. And in any case, so as you notice here, that if we amortize the calendar and a single iteration like this, where we may have a batch, but then we are estimating phi for a larger number of variables versus we are estimating theta, which is global variable across all entire data set, we might err on the side of estimation of phi, or we may have to do a lot of iteration to get the right estimate for phi, which may defeat the purpose of this inference network. So then there are these techniques called semi-amortized inference, where instead of estimating phi and theta at the same time, you have a warm-up cycle where, and I'm looking for the term warm-up, which I did not highlight here, but you essentially are trying to warm up for size early on, and then start the amortization step. So that is essentially the amortization gap that you may induce because of the optimization you did in algorithm 10.1 to reduce the number of cycles for estimating the psi through phi. So now, one of the easiest things to think about phi network is to, or optimizing phi and theta, is basically derive those point estimates in our case. Those are fixed variables, phi and theta, which, I mean, z is a random variable, but phi and theta are point estimates that we are trying to derive using elbow optimization. So one way to think about that is we take the derivative of elbow and try to find what is the best way to get theta and phi, and that's where the gradient-based VI comes into picture. The simple equation for, and I'll go forward, please, we'll come back to this picture, but essentially the simple optimization that we have to do is to find both theta, which is under my cursor here. So we take the symbol is called what, nebula? I forgot the term. Anyway, so we take the partial derivative with respect to theta of elbow, and we take the partial derivative of elbow with respect to phi, and then we are trying to, an iterative step as shown in 10.1, optimize, find the theta and phi. But in this case, we'll be using the gradient mechanism. So applying this gradient to elbow, you can go through the steps or look at it later in the recording, but essentially you can see, and I have some notes also, you can see that it is possible to get the theta estimated pretty easily with this expression, where ZS is a sample that you pick from the latent space defined by this distribution. Note that this is an unbiased estimator of the gradient, so you can apply SGD. So essentially you can do the gradient descent, stochastic gradient descent. However, the gradient with respect to phi becomes tricky because over here, when we were doing gradient with respect to theta, our expectation, elbow has expectation with respect to network defined by phi. But here, gradient and the expectation is with respect to phi. So it's not possible easily to compute this gradient. And therefore, we cannot take the expectation out and push the gradient inside. So that is the core of our all the VI problems on how we can solve for this piece. So what you would notice in different solutions that are provided or discussed or new things that come up are trying to push this gradient inside the expectation. So maybe oops, sorry, I don't know what I pressed. Okay. So because this is not equals to this one, so there are different tricks that are applied. And one of the tricks that is applied to estimate the phi network's parameters is called reparameterized VI. And let me show the picture now. I think the context is set for it now. So this was our model where F is our elbow that we are trying to optimize. That F is based on the input parameter and the phi, which are the fixed point, but of course we'll have our derivative be optimized for phi. So from phi network or the parameters, we estimate Z, and then from Z we take a sample, and from that sample we get the elbow, and then we try to optimize for that value. And when we're trying to optimize for that value, when we have to take the derivative can pass through to Z, but then because that's a sample, random sample picked up from this distribution, there is no way for us to find the phi from this one because that's a random sample that we picked up, and we cannot have the derivative propagated here. So one of the tricks that is applied for we cannot have the derivative pass through the random node. So the notation is that this blue color is a random node. So one of the tricks for reparameterization is that we define another random node and introduce parameter epsilon, which randomizes Z. So we use the value, whatever Z we have here based on our phi, but we change the parameter from Z to based on phi, x, and epsilon rather than Z only. So if you see the change of variable that we applied here, instead of Q, Z dependent on X, by introducing this random node, which is with its own distribution, this random node is now becomes a fixed value based on the, of course, the function here, but it's a function of phi, x, and epsilon, and then we can pass the gradient along to optimize or find F. And there is a lot of math involved in the explanation for how that works. I'll not go into that, just quickly point in this particular paper or this book where they have that math discussed. Feel free to look at the details later on.
Hey, Dave.
Yes, go ahead.
So if you can scroll back up to the diagram, yeah. So there's actually something that I realized when I was rereading this section that I didn't appreciate about the reparameterization trick until the author, explained this. So if you just talk about a regular one-dimensional Gaussian distribution, okay? If you know the mean and the standard deviation, you know what that Gaussian distribution looks like, okay? So if you have a mu and a sigma, you know the Gaussian distribution. And so if for your if your phi contains a mu and a sigma, and your epsilon is just a unit Gaussian, right? Mean zero, um, uh, standard deviation 1, then basically what you can do is you can just take the epsilon, multiply it by the standard deviation, add the mu, and it's the same thing, whether you sample from mu and sigma or you sample from 1, 0, and you just do the multiply and the add, okay? So I'd seen that many times, and I was like, oh, yeah, great, that's cool. The thing that I glossed over is that you are doing a change of variables, okay? You're doing a change from the original distribution to this, and so what's involved is, okay, that's a simple way of explaining it for a unidimensional distribution. But just to use round numbers, what if we have 1,000-dimensional distribution? Okay, then I'm going to have 1,000 mu's. That's pretty reasonable. That's tractable. But if I want the full covariance matrix, I need to have 1,000 squared. I need to have 1,000,000 entries in my sigma covariance matrix. That's why you see that there's this whatever independence assumption, and they say, oh, well, let's just assume that the covariance is diagonal, and then I only need 1,000 diagonal entries on this sigma covariance matrix. Okay, but the problem is that does then introduce a simplification, and it's a limitation on what your Q distribution can now look like. So in the two-dimensional case, if you have a diagonal covariance matrix, then your Gaussian can basically look like a circle, and can look like an oval that's vertical, and it can look like an oval that's horizontal, but it can never look like an oval that's diagonal. Okay, so and that's just the 2D case. So in the typical, 100, 256, 512D case, there are a lot of possible ways the distribution could look that you've now excluded by making every one of your components independent. So in the section, it goes into more rigorous detail where they talk about the change of variables theorem, and so then basically it's the determinant of the Jacobian. But just know that basically you either have to deal with all of that and keep track of sort of like n squared, sigma components, or else you can brush it all aside if you do something like the diagonal, which is much faster and easier. But then, you may run into some issues. So did I say all that right, Dave?
Yes. Only other thing that I'll add is, and if I may go back to the picture, which may kind of show what you were saying, is equation 10.37 is the change of variable equation, where if you are sampling Z from a Gaussian with mu and sigma, it could be anything between mu plus whatever sigma, whatever, based on the distribution, you'll get that. However, with Z modeled as mu plus epsilon, dot product with sigma for multiple dimensions here, where epsilon is the new random now with standard Gaussian, then all I have to do from my network phi is to estimate mu and sigma, and whatever those values it comes. Now that variability is gone, it's just those two numbers, and all the variability or the randomness is coming from the term epsilon here, which we are not going to backpropagate to. So we will backpropagate to mu, which is a fixed number that phi is estimating. We'll backpropagate to for sigma, which is again a fixed number for that distribution. So those parameters are fixed, and we learn those, and we will not backpropagate to this one. And through the mathematical change of variable theory, as Ted mentioned, which you are free to look at in this book later on, there is a clear determination that why this will work. And how in that case, if you remember from the previous equation that we had for the elbow optimization for gradient through phi, now changes to gradient of phi through this expectation, where the expectation is now not based on the distribution for z, but for epsilon distribution. And that is, then you can push basically a gradient inside. So this is the optimization that is done here, and reparameterization trick that is done here. Sorry, Ted, you were going to add something. I continued there.
Yeah. And if you look at that equation 10.37 that you were just showing, you'll see that on the far right, it says epsilon is sampled from a normal distribution with zero mean and diagonal all ones covariance matrix. So if you assume that mu and sigma are constants, then this is just a univariate distribution. But if you assume that mu and sigma are vectors, so then if they're vectors 100 long, now you have a 100-dimensional distribution, and so you're sampling it from a vector 100 long of zeros for the mean, but that covariance matrix is a 100 by 100 square. And in this case, it's an identity matrix with zeros everywhere off the diagonal. So that's that, one of the simplifications that we make. And so this is one of the places where, again, you can say that we're going to, like you run this and it converges, okay? But just because it converges, you still don't get to a zero KL divergence where your Q is identical to your posterior. And so this is one of the places where we're going to limit the ability for our Q to exactly match the posterior, okay? Because it's only independent variables with the diagonal covariance matrix. And that limitation could potentially cause our minimum KL divergence to not be as small as we would like. And so therefore we have a poor estimate of the posterior. And maybe what that means when you build like a variational autoencoder to generate images, maybe that means you get fuzzy images. There may be another reason for the fuzziness, but for example, that's, if we had perfect fidelity in a zero KL divergence, then we should be able to absolutely generate perfect looking images.
Yeah. So, also want to add that, so essentially it boils down to the design of this transformation that we see up here, which was the equation 10.37. So that is the key equation, of course. And then because of that, the translation here in 10.40 is important. But the reason 10.37 design is important, like in this case, they are assuming Gaussian, right? So original Z is Gaussian. So what you see in the next two sections, 10.21 to 10.2.11 and 10.2.13 is that, hey, what if my Z is, and if I go just a little up, is a diagonal covariance, right? So which means that all the sigmas are independent for the latent variable Z. Sigmas are, there's no, covariance. Or what is it called? So it's diagonal covariance. So there's zero covariance between variables, variance between variables. And with that, what they show subsequently is that you actually get the derivative for your function elbow, which is like you see this term log theta this plus dkl, and I looked at it, but I have forgotten since I saw it, but essentially it comes down to a very simple expression here. So for whatever sigmas and mu's that are being estimated by your network for phi, your essentially the term is very straightforward in terms of the loss that you have to look at, and you're trying to optimize for that. So for the diagonal Gaussian estimate for your Z's, when I say diagonal, what I mean is, of course, that all of the sigmas are independent, essentially. So they are not, the Z's are independent of each other. However, if there is a dependence between them, then also you can use this Cholesky decomposition form, but of course it gets costlier as you have more and more dependency. So if your z's were if you look at equation 10.52, if that's how z is defined, then also there is a relatively closed form expressions that you can get, but you're finding L and doing the decomposition is a very compute expensive job. So there are, as you can see in 10.2.13, just like our LoRa thing, there is a low rank diagonal covariance conversion. So I will skip all of those things, but there are these techniques depending on how your Z is modeled. So you typically, if you are modeling Z all independent, no covariance between them, then you will get more fuzzy images. If you model covariance, then you have to pay in terms of compute, and then there are tricks to help reduce the compute cost.
That's well said, Dave. So basically what we're saying is you can model more generally at a compute cost, or you can model less generally much faster. I can't really speak to too many of the details, but my guess is for any problem that's like this, right? If you were working on this and I was advising you, what I would say is, yeah, do the simpler one that's less compute first and see if you get a pretty good answer. So if you do the simpler one and you want to do a variational autoencoder to output kittens, like if your kitten pictures look really good, you're done. Don't even worry about the more complicated thing. But if you're like, oh no, it doesn't look that good, then it's like, oh well, why don't you try these various increasingly more expensive versions? I'm guessing that would be sort of the high level rubric.
Right. Thanks, Ted. So that's for the reparameterization trick, and there are other variational posteriors. I don't know what they mentioned there, just 2 paragraphs. Well, I'll skip past. I mean, as you can see, they do refer to some of the new works all along the book, and that's the best part, that this whole field is moving really fast everywhere in all dimensions. All right, so this section that I have here is highly dense in terms of my words here. Let me see if I can very quickly give a high level idea on what is happening here. So we used in this section, they are using the reparameterized stochastic variational inference to infer the posterior for the parameters of the Gaussian mixture model. So Gaussian mixture model has 3 latent variables. The for each of the points, the assignment to each of the clusters. Then for each of the clusters, they have the mean and the variance. So those are 3 parameters, which are the latent variables that need to be modeled. We will marginalize the discrete latent variables. So the discrete latent variables are, in this case, all these are the I think what they are saying here is this is the original model, and they want to model it as a collapsed model as shown over here. So all these discrete latent Z1, Zn, and theta are modeled as one single set of theta as shown in this picture. So that's what it's saying. That is, we have converted the model in figure 10.5b to the one 10.5a. That's what we just saw. And then they assume that we'll come to this mean field variational very soon, but essentially they assume that each of these parameters are independent of each other. So if that be the case, you can model the likelihood as a product of each of the variables, random variables probabilities, right? So the total probability is based on the each of the individual individual data points probability. And in this case, they are going one step at a time. They're first doing the probability for the cluster, and then they further go down for the probability of the each of the data points here. But what they are also trying to model here is the variability in your parameters. So uncertainty in your parameters. So your parameters themselves are actually not fixed points, but are a distribution. And if they are distributions, so let's say in this case, and I've tried to note it down here. So if my so my assignment to each of the clusters is a multinomial categorical assignment, right? For each data point, I want to assign it to the cluster C, and the prior for that variable can act. If that variable is not a fixed point but a distribution, then the prior to that would be a Dirichlet. Similarly, for our each of the clusters mu and sigma, if the given that we're doing mixture of Gaussian and this is the posterior that we want to model, the prior for the model is this. But if we want to have for these variables mu and sigma, if we want to if the priors are not fixed points but a distribution, then that will correspond to the I think it is called gamma function or something like that. That's the core concept that needs to be understood for this modeling, that how you're trying to model the uncertainties of the parameters themselves. And with that, what you're trying to get to is to optimize your elbow. And what they showed was that you had much better handle on the assignments of clusters or the identification of clusters with the variability as is shown in this, that, well, this is what my mu and this is what my sigma distribution looks like for this cluster. So given these data points, which are 3 clusters, this is how the uncertainty around the mu and sigmas is also modeled here. And then for a specific, in this case, they picked up this particular cluster that it's not showing very clearly, but the lower cluster, and they showed that how the uncertainty contours for this look like. So they've just shown this specific one over here in detail. You can read more about it in the book, but essentially that's what this section is trying to help highlight. And that's why, if I may just show the title again. So this is the parameter inference. So not the variable inference, but also taking the parameter itself as a distribution rather than a fixed point. And that's what it is trying to do here.
Hey, Dave, can you
Yes,
refresh my memory? So when you do the standard EM algorithm for a Gaussian mixture model, which like all of us, like you can just call it from scikit-learn or whatever, that just gives us a point estimate. Basically, that tells us where the cluster centers are or whatever, right?
Mu and sigma for each cluster. Yeah.
Right. But there's no uncertainty around mu. That's just giving us a point. So it's saying, here's my best estimate for mu, but I have no idea what the variability in mu might be. Is that correct?
That is correct.
However,
so
what you just did on this page is giving us a distribution of possible mu's so that we can actually have a credible interval or whatever we wanted to understand the variability in both our mu's and our sigmas.
That's correct. And I probably did not use that term clearly, so thank you for clarifying it. Is what you see in B is the posterior mean distribution. So the mean is most likely this yellow piece in the middle, but
Right.
there is some uncertainty, and the mean could be in this whole region.
Yeah, and so I don't I don't know enough to know. I think we would get the exact same answer if we just did the EM algorithm to get the point estimates. We'd get that same mean. But I just want people to be clear that what we have is a lot more than just what's shown in figure B. We have that, and we have the density around that point estimate for how sure are we what that mean is. And then the standard deviation, tells you, if you look at the, I don't even know what to call it, the yellow-green fuzz, right? Should it be a very small little fuzz, or should it be a very diffuse, large fuzz? We have a point estimate for that, but again, how sure are we that the circle should be that fuzzy? Could they possibly be a lot more or a lot less fuzzy than what's shown in figure B? So again, no, for just this Gaussian mixture model, I don't think having the distribution instead of point estimates is like earth-shattering, but I think it at least proves the point that there is a difference between VI and simpler techniques.
Right. And while the simpler technique, EM may be all, the vanilla EM, in this case for mixture of Gaussian may be good enough for most cases, but they will highlight subsequently how sometimes that can be not very helpful if we do not capture the uncertainty in some cases. So anyway, so that's one part, but I think that in the context of reparameterization trick, what they also highlight here is, because we are trying to estimate the parameters variation here. So this is the elbow that they determine for where psi are the hyperparameters, which actually are the parameters, if you may, to model the uncertainty of the GMM parameters. And they show in algorithm 10.2 that they actually applied the reparameterization trick where they instead of so whatever were the parameters in that specific, so instead of psi here, do they continue to use psi? They still continue to use psi. So the latent variable is not random in this case, and I apologize, I did not do due diligence in trying to highlight how this reparameterization trick is applied here, but essentially it is the same 10.1 algorithm or whatever we saw for the reparameterization trick.
So Dave, what they're doing is, instead of directly sampling from their parameters theta, is they're sampling from line 4 epsilon, and they're calculating an approximate theta based on their sample using that G conversion, which for Gaussians, you just multiply with the variances and you add the mean.
That's right. So, and then they continue to update the different parameters of your original in this case, the point estimates are your parameters essentially, and then find the parameters themselves based on that. All right. So I will skip past some of these sections. Again, these are more details and different kinds of reparameterized, amortized SVI, which is actually what we'll read anyway in VAE. So I'll skip past. All right. So one of the this section 10.22 talks about automatic differentiation, and one of the key things that we saw above was we are using sigma, but sigma is it's constrained in the sense that it cannot be negative. And when we do gradient-based analysis, sometimes we can have where values are predicted to be negative, and that may break our whole model. So, and that's just one example. So there are tricks that are applied so that you can leverage differentiation in VI without having to worry about those constraints. And there are transformations that are applied so that you can continue with your differentiation and get your optimal values for parameters with best possible optimized values without having to worry about those constraints. One example is I mentioned about sigma. So one transformation that is applied for variance is to take the log of that. And now it can be negative and positive, and it can easily go in different directions. And that's what my note here says that essentially that's exactly what it is. And more of my notes here to explain the same thing. And that's what ADVI is about. They went ahead and applied ADVI for GMMs. Given the time constraint, I will skip past this section for now. But feel free to read this notes or recording later on.
Yeah, I think this is really good, Dave. So I love your example where like standard deviation has to be positive. So what's a transform that allows us to predict something that's over all reals, and then we'll just apply the inverse function in order to recover our original parameter that's positive only. So we've got about 15 minutes left, and so we don't have to go into any detail. I think if you can just sort of high level, if you have any takeaways that just sort of say like, yeah, if you're willing to add more complexity and more compute, then there's the possibility, you get a better, this section talks about you might get a better result because you put more oomph into this part of the process.
So this is what I'll do. So for each of these sections, just like how I covered the ADVI part, which was like 1 minute or 2 minutes, let me cover the rest of the book that way, because the core concepts, if we understand those, are easy to apply to rest of the sections. Of course, there's a lot of math detail and devil is in the details. So we are not going to go through all those, but if we understand the core VI concepts, the rest are just building on those core concepts and not as complex to understand. So is that an okay plan with you, Ted?
Yeah, that's perfect. I mean, I don't know if it can be done easily, but yes, if you can break down each section to just like 3 sentences and just say, here's the gist, then yes. If we need to, we can always come back, we can read in more detail, but right, we have the main concept. This is just tweaks that, again, allow us to possibly get a more accurate estimate if we're willing to dive deeper in these various places, typically.
Right. So this next section, 10.2.3, talks about the black box variational inference. So the main reason or places where it is leveraged is when, so far we saw the example with the parameterization trick. It was easy to apply in case where C's were relatively easy to compute or tractable, so you can have your losses defined more easily. But more often than not, your distribution is more complex. So, and in particular, if it's non-exponential family, then the distributions prior and posterior calculations become very difficult. That's where the black box variational inference tricks are applied. And these are pretty common and applied pretty lots of places. So for example, the reinforced technique using the score-based estimation, score function estimation is what diffusion model also uses, but I'll not go through that, but essentially that's where the black box variational inference is applied. And if you recall that we had this gradient to the expectation function, but essentially what this does is takes the expectation function out and pushes the gradient inside, and that's the whole, as I said, the holy grail for the next levels of Elwood determination. So that's what these black box inference techniques are about. And score functions we'll cover even in more detail in our future, hopefully in the diffusion section as well. And then there are covariates that are leveraged to find the function estimate that can get us a better or more tractable elbow without going too diverse, so containing the variance essentially. 10.3 is an important section, and maybe I'll spend 3 minutes on it. So coordinate SNPI. So this is also called CAVI, C-A-V-I, an approximation that is used when you assume that all your latent variables are independent, which means that the distribution for the latent variable Z can be just the product for all individual latent variables. And this is a pretty common technique that is applied in many places. We'll see that in future sections, and may have seen that in the past as well. With that assumption, a lot of the derivation on how you estimate each of the parameters for ZIs becomes easier. And it boils down to the simple equation that we see in the algorithm here, where essentially you initialize your in all the ZIs as shown here. You initialize, then for each time step, you go through each of those ZIs and compute individual ZIs based on the Markov blanket of your model that you have described using this function. And the derivation of this is defined in the previous derivation formulas up here. And then you compute the gz function, which is defined over here somewhere up there, and compute the qj function, which helps you get the distribution zi essentially. This is a very common technique because it makes the computation really fast and easy. And SVI, the stochastic variational inference, initially used the mean field approach in the past. So I will, again, not go into details of that. As I've mentioned earlier, this is the freeform VI. I will not go through the example here, but again, there's a lot of math to just showcase it works for the icing model. But the core concept is that the latent variables are all independent. So the distribution is the product of individual latent variables distribution. And as mentioned earlier, if you treat theta as the latent variables, then the whole new modeling comes in. But if you assume that those are all independent, then you can assume that the variational posterior factorizes over the parameters if it is a mean field variational inference estimation. And then you can apply the VB for a univariate Gaussian. And again, we are trying to estimate the parameters of the parameters in this case, and we are assuming that those are all independent. So we say that mu and lambda are latent variables, and then we apply the mean field, and then we can apply CAVI2, which is the coordinate ascent VI to estimate that. Again, a lot of math to describe for different parameters. Mu and lambda is actually precision, which is sigma inverse, computing the expectations. All of those become pretty relatively straightforward, and you can have your network just try to optimize for those. Here is that example where we are trying to estimate the parameters. They show, like, if we have this, let's say this is the exact, the orange color is the exact distribution. Then using the multiple steps to, in this case, I think B is the distribution for mu, assuming psi for mu. C is the precision. And then after you go through multiple steps, it's pretty good close convergence to get the original distribution. It works in some cases, mean field, if you again, these are the assumption of the models, and you have, people make those assumptions based on their understanding of the models.
So Dave.
And yes.
So just super briefly, so in this case, we
Should I go back up?
no, I don't think I have anything specific to reference, but so in this case, we have traded off. First, we were talking about sort of this fixed VI where we assume, like say, that our Qs are Gaussian or whatever, and that's a simplification that allows this to be tractable. In this case, we don't have to assume that functional form. We have to make a different assumption. We have to make an assumption that the Qs are independent. And that simplifies the math and allows us to be able to compute this tractably. Because if you look at the I don't know, is that blue, green, whatever that is, but the blue predicted distribution is not a Gaussian. That is not a simple oval anymore.
Yes.
Right. If you look, the bottom is more scrunched and the top is more spread out. It's and so that's what this allows you to obtain that. If we had done the first, it would not. It would have been strictly limited to an oval shape.
Gaussians, yes. And this is the Gaussian gamma distribution. The specific orange distribution is the Gaussian gamma distribution. So we are trying to estimate that. And by assuming all the latents independent, we are able to get to very close. But that's a strong assumption. All the latents are independent. If that holds true, then yes, it will work in your favor.
Yeah, I think it works better than it might. Sorry, I'm taking up your time. Just because, you know, if you think about it one way, then certain things might not be independent. But if you decompose the latents differently, then you might be able to have latents that are actually much closer to independent of each other.
Yes.
Right.
And I think in this case, yeah, their actual distribution, the final thing is Gaussian. So that's why the prior is, or the conjugate is the Gaussian gamma, and there is no, you know, easy, relatively easy tractable way to get it. And yes, there is a conjugate prior, but again, the tractability doesn't exist. So they assume in this case, they tried mean field, and for this case, it works. Yes. But you'll see a lot of examples out there where it just, I think we saw it one example last week also, where it was miserable because there was dependence between the variables. Very quickly, so they applied this VBEM to GMM, and the same things apply. They are trying to estimate the parameters. I'm skipping past really fast, and I'm sorry if it is dizzying to see that, but one of the effects that they showed here was that the Z's, for example, different Z's, they either, you know, converge, like, you know, they basically have either very strong affinity. So Z in this case is the assignment of each node to each cluster. So either, like, as you go to the number of epochs, they get stronger in terms of their affinity to a cluster, or they say no very soon. Versus the original, I think X in this, on the left hand side, they are showing, this is, I think, the overall trend, and these are the individual latent variables. And for the blue line in this example is what they are showing is how the assignment actually shrank for the VBEM. And then, you know, this is, I'll just skip past this, just too many details. So that's the core part about that. This is again trying to go through some of those VBEM examples. You can have the variational inference for the message passing, and again, you can have the Kavi applied there as well. The message passing is what Christian has covered in the previous chapter. So you have the, you know, some kind of blanket or dependency on some other variables, and you get your probability distribution based on that. And once you have that, you have, just like you have the automatic differentiation technique, there are auto-conjunct techniques for the variational message passing. Yeah, there are more techniques on more accurate VI, structured mean field. I did not even read that, but some they are referring to the future section, so I felt comfortable skipping past those. So, for example, this hierarchical posterior is in chapter 18, normalizing flow is in 23. This is in chapter 26. Uh, I know that Ranjit asked a question about sampling techniques for so this is where, again, we'll talk in chapter 12 about this as well, combining VI with MC inference. And I think this was one of the pet questions from Janine. I'm sorry, I forget the name, but one of the persons who used to attend. In this section, instead of relying on the single sample, they take multiple samples and figure out what the value should be from the second part of the network, and basically that's what they call it, importance weighted autoencoder. So instead of taking just one sample, they take a weighted sample in the middle part of your network, and that's what the multi-sample elbow is. They find that it works sometimes, but again, all of these come with a caveat, and refer to the chapter for when it works, when it starts to fail. Sometimes they found that it can decrease the signal to noise ratio and resulting in a worse spot. So they all come with their caveats when they work. Again, this is somewhat empirical as well, but these are different techniques for optimizing your elbow and figuring out which one of those works best. In this section, they talk about, instead of maximizing the elbow, what if the lower bound, what if they find the upper bound on your evidence? And they change instead of negative KL, they have reverse the KL, so P to theta, which is, I think, one question that was asked 2-3 weeks ago. What are different ways of using divergences here? And again, they have caveats. For one, they have the description of the whole algorithm below, wake-sleep algorithm, based on that. But again, just like other sections, it comes with the caveats on when it applies and when it doesn't. More than that, I think what are the places, what are things that go wrong? When and which situations is hard to predict, but definitely, not a panacea for the challenges that we have with VI estimation. This is the same wake-sleep algorithm that is part of the EUBO, the evidence upper bound. And then this is the interesting one, 10.7. So we generally try to do the reverse KL optimization. What 10.7 is trying to do is the forward KL for P to Q optimization. And the reverse KL, which we have Q to P, basically will avoid the situations where PZ is 0, then it will just, basically it will capture one of the modes and just stick with that. That's what reverse KL will do. If you have multimodal probability distribution for a posterior, reverse KL will find one of those and stick with that, because that way it can avoid the situation where PZX is 0, but your QX is non-zero, then your KL will become infinity. So that's how it tries to avoid that. I have a little slide which I can just post in the end and not really talk about it. But essentially, expectation propagation is a technique which does the reverse KL or the forward KL optimization. They have some algorithms for that. And again, mixed luck is what I would say with this algorithm as well.
Yeah, I had a question here. Yeah, so if you took this and we're saying 40,000 floats in a computer that can run, thousands of images, same exact data set with this, what would be some of the main trade-offs? Is it, because Ted mentioned more complex, more compute, are you going to lose, be worse in loss, accuracy, those types of things? Is there a judge for that? Like, has anybody done like a small experiment to see, is all this kind of worth it?
So yes, this is definitely a very open field in terms of what works and what does not. So that's a great question, Kevin. In terms of complexity, all of these techniques, this whole chapter or section is around finding the techniques to infer the posterior, right? The complexity of algorithms will increase from some Laplace approximation, which is really quick and fast, maybe to all the way to sampling, which is very costly. So depending on your problem set, depending on how you understand the problem space that you're trying to model, because at the end of the day, it is highly attached to how you model your original problem, the probabilistic graphical model, and how you estimate the data that you have there relates in terms of the latents that it may be there, or the original modeling also that exists there. So it's highly tied to that. Having said that, the reason people and all these techniques and tricks that you are seeing here have been, I would say, released in the last 10 years or so, and more and more are coming out as we speak. I'm not giving you a very confident answer in terms of what will work and what will not work. And the only reason for that is because they all come with their own caveats, and people have found that, well, some of these, like the ones you have in GANs and VAE, those work fine. But depending on the complexity of problem, like for images, I don't think people are even applying any of these EP or even for that matter, VAE as we in current day and time. They are all moved on to GAN-based modeling and diffusion based modeling, which uses some part of ELBO as a optimizer function objective, but score based modeling is also what is used here. So long story short, it's a very highly evolving field. VI is applicable to certain set of problems where the model is easy to understand, but for images, I think the convergence is more around GANs and diffusions, if you may.
Okay.
And I don't know, Kevin, if it helps answer, but that's my high level take on it.
So let me just jump in and say, so my general answer to that question is you should always measure the effectiveness of your model against your business objective. So even when we're doing something much simpler, like, oh, I'm building a model to predict how long my patient appointments are. I could do linear regression, I could do a gradient boosting machine. Yeah, we all know that we learn certain things like mean squared error or whatever, but the true differentiator is how does that impact the business? So in one business case, you may find that a 2-minute difference in error is nothing. And you're like, yeah, so therefore, even though the gradient boosting machine was more accurate, linear regression was much faster, simpler, interpretable. So we're going with that. In another one, you're like, no, 2 minutes is $500 million to me. I'm going with the gradient boosting machine, right? So in this case, I would say if you're using this technique because you want a generative model, let's say for images, what you see in all the research papers is they then use some metric, to say how good are these images, right? And so at the end of the day, that's what matters, right? So you may have blah de blah measurement of whatever, but it's like that doesn't look like a dog. Then your model sucks. It's at the end of the day.
Yeah, that helps. Thank you.
So that's mostly about it. I think the only thing that I did not speak, and maybe a couple of sentences, was on the upper bound optimization. I think the wake sleep algorithm works slightly differently than other VI algorithms, but again, the section 10.6 of the book is pretty, if those are just 2 small paragraphs, and they talk pretty easily and nicely and clearly about especially the second paragraph on, and I can just show here what that does. But again, since we are not going to cover the details of that right here, they are basically optimizing the generative parameter model theta to maximize the likelihood in one step, and in the second step they optimize the inference model parameters. But those are totally independent networks, and unlike the other VI models. Again, feel free to look at that offline, but this paragraph is what is most important about that. That covers this chapter.
Awesome. That was a really good rundown. So Dave, I haven't seen this wake sleep algorithm referenced in research papers, at least not by this name. Maybe it's sort of like hidden in the math behind the scenes. Do you know if there's a place where this is used in something that we all would have heard of?
No, and you're right. It's not very common. And one way I have figured what is important and not important is also based on the references. If I don't see newer references, there's one, yes. But if I see a lot of references or forward chapters references, then I know that it is being used a lot. So short answer is no.
Cool. Awesome.
I just want to say that third time is a charm. So thank you for staying with me for 3 times to get it through.
No, I appreciate this rundown, and as I've shared with people before, it does take sometimes a little bit of time and a few repetitions before things kind of sink in for me. So, thanks for joining us today. What we have up next is we have a somewhat shorter chapter on Monte Carlo sampling, and I don't know, I haven't read the chapter yet, but Ranjit has volunteered to lead us through that discussion. I think what we're going to find is if you just vanilla try to randomly sample to estimate your posterior, you're going to have a really hard time, which is why 2 chapters from now we have Markov Chain Monte Carlo, and MCMC is used a lot. I just don't know if it's used a lot in like deep learning, machine learning, but it's definitely used a lot in general in order to estimate things in lots of different fields. And then there's one more chapter at the end, and then we will be done, and it'll officially be summer for our group. And so then we can have a discussion if we're going to talk about part 3 of the book. But that will wrap up this official section of the book.